In the first part of this video lecture, what we have seen that if a sequence of functions converge in LP on any measure space, then they converge in measure as well. And then we saw also that on a probability space, or for any finite measure space, you can do that just by multiplying the measure by a constant. On a probability space, we have if converging in LP is easier than converging in LQ for a larger Q. Or let's say if a sequence of random variables converge in L2, then it converges in L1. If they converge in L3.5, they converge in L3, and so on. And we saw the proof of that. And now what we may start asking is, what about convergence in LP and almost sure convergence? What can we say about that? Well, here's an example that converges to 0 almost surely, but does not converge in LP. And what is the example? The example is very simple. We have 1 over n here, n here, and we have this function. And you see this function, as we make n larger and larger, it amounts to a rectangle that is just getting thinner and thinner, but at the same time taller and taller, so that its integral is always equal to 1, even though its value converges almost everywhere to 0. So see, this function converges almost everywhere to 0, but does not converge to 0 in LP. And it cannot converge to any other function in LP either. So from this and previous examples that we saw in the previous unit of functions that did converge in LP but not almost surely, an example would be, for instance, the traveling wave. The traveling wave function, the dancing wave, as it keeps traveling again and again, it does not converge almost everywhere, but because the measure of this set is so small, it does converge in LP. So in summary, it is possible to converge almost everywhere, but not in LP. And it is also possible to converge in LP, but not almost everywhere, even in probability spaces. So almost sure convergence does not imply convergence in LP, does not imply, and convergence in LP does not imply convergence almost everywhere either. And we can deduce more from this simple observation, because, well, we have seen before that convergence almost surely implies convergence in probability. And we have seen that convergence in LP also implies convergence in probability. But now, since we see that these do not imply each other, it also means that convergence in probability do not imply any of them. And why is that? Well, we can argue backwards. If convergence in probability did imply convergence almost sure, then convergence in LP would imply it indirectly, because it implies convergence in probability, and from there you could go to convergence almost sure. Okay, so again, what I am saying is, if this implication would hold, then this implication would hold by going this way. And likewise, if this implication would hold, then this implication would hold by going this way. So we can conclude that none of these implications hold. Neither this one, nor this one, nor this one, nor this one. None of them holds in general. However, we have seen that if there is convergence in probability, then we can take a subsequence. That converges almost surely. And now, between convergence in probability or convergence in measure and convergence in LP, is there any circumstance where from convergence in measure, we can conclude convergence in LP. And this is the topic of the next theorem, which is also the last theorem of this video lecture. And the theorem says the following. We can also call it dominated convergence theorem. It's just a stronger version of the dominated convergence theorem. And it says it's valid on any measure space, not only probability spaces. And we take a sequence Fn of Borel functions, and we assume they converge in measure to another Borel function. And how can that imply convergence in LP? Well, that will imply convergence in LP if there exists a function in LP such that all these Fn's are dominated by it. So that's why we call it a still dominated convergence theorem. And in that case, we can conclude from convergence in measure, we can conclude convergence in LP. And as we have seen already, convergence in LP implies convergence of the integral. So we can conclude that the integral of Fn will converge to the integral of f. So this is the last theorem of this video lecture, and we are going to make a video just for the proof of this theorem.